Look closely at legacy AI video models to identify a persistent structural flaw. They operate by generating silent, independent two-dimensional frames, one after the other. To create motion, these systems attempt to stitch those isolated frames together through interpolation. The math forces the software to guess how pixels should transition, yielding the familiar hallmarks of early AI video: subjects morphing into their surroundings, and objects moving with a floaty, weightless physics. Because they only calculate visual data, these systems also mandate a disjointed production pipeline, where all audio synthesis must be engineered and synchronized after the fact. The researchers at Google DeepMind took a different path with Veo 3.1. This latent diffusion transformer abandons the two-dimensional frame-by-frame approach entirely. Instead of stacking flat images, Veo 3 treats time as a physical third dimension. It processes audio and video latents simultaneously. The model does not look at frame 1 and predict frame 2. It calculates an entire 8-second, three-dimensional volume as a single, continuous physical space. By calculating this full spatial temporal volume from the start, the transformer locks the geometry of the scene in place. The morphological artifacts and warping that plague interpolation models are mathematically prevented. Shifting from flat 2D interpolation to true spatial temporal simulation removes the randomness from the output. It turns AI video generation into a reliable component for strict engineering pipelines. To understand how Veo 3 enforces this physical consistency, we must look at how it handles data. The architecture first compresses raw video and audio inputs into lower dimensional representations, shrinking the computational load without losing the structural detail. This 3D tensor grid illustrates the diffusion process. Instead of denoising a flat image, the model resolves noise into structural data points simultaneously across all three axes: height, width, and time. A mechanism called cross-frame attention operates across this entire dimensional volume. It maps how a single pixel, or audio frequency, relates to the rest of the sequence, maintaining strict consistency. It also utilizes dedicated memory banks to store important visual features throughout the generation process, preventing subjects from flickering out of existence as the seconds tick by. For movement, Veo 3 relies on motion vectors. Rather than guessing pixel placements frame by frame, it predicts the natural trajectories of objects traveling through the 3D space. Trying to guess the next single frame in a vacuum requires the model to hallucinate details constantly. Calculating the whole space at once means the end of the motion is already informing the beginning. This long-range dependency modeling allows the transformer to natively understand the complex physics of resistance, gravity, and momentum in motion. By mathematically binding spatial and temporal data together during the initial diffusion phase, the architecture guarantees object permanence from the first millisecond to the last. That temporal axis serves dual purposes. Veo 3 integrates sound directly into the diffusion process, generating it alongside the pixels rather than bolting it on afterward. This diagram shows two parallel data streams: visual spacetime patches and temporal audio info, entering the transformer core during the denoising steps to be processed as a single coupled dataset. The model learns how to map these two modalities together by studying millions of hours of training data, which Google captioned using its Gemini models to explicitly link visual actions with their corresponding sounds. The specific output of this joint generation is AAC-encoded audio at 192 kilobits per second and 48 kilohertz stereo, synchronized perfectly to a 24 frame per second motion picture. Coupling the data streams requires heavy computation. Running the joint audio-visual generation increases processing time by roughly 25 to 30% compared to silent output. Storage overhead also scales up. Because of the density of the combined spacetime and audio data, the resulting file sizes are approximately 3.2 times larger than video-only generations. Engineers explicitly trigger this sound generation in their text prompts by wrapping dialogue in quotation marks and providing descriptive text for Foley and sound effects. The model uses scenic context to produce perfectly aligned ambient noise, calculating a ceramic impact's exact sound based on visual velocity and surface tension. Generating the latent audio and visual data simultaneously eliminates the manual Foley and syncing bottleneck, stripping hours of labor out of standard post-production timelines. Accessing this architecture at scale requires programmatic integration. Developers interface with Veo 3 using the Gemini API to bypass standard chat interfaces. As seen in this split-screen layout, the API allows engineers to force deterministic outputs. Rather than relying on open-ended text prompts, developers pass structured JSON payloads to lock the 3D volume into specific boundaries. Using the Ingredients to Video feature, a developer can pass up to 3 images into the reference images array. The model analyzes these assets and explicitly locks the subject's appearance across the generated timeline. The model also exposes exact interpolation controls through the image parameter for the first frame and the last frame parameter for the final frame. By explicitly declaring the start and end states, you force the model to calculate a precise transitional 3D volume that mathematically links the 2 fixed points. The text strings within these payloads adhere to strict syntax. Camera movement, shot type, and specific lens characteristics must be explicitly declared, or the model defaults to a flat, generic framing. Enterprise brands are utilizing these programmatic constraints. A company like Virgin Voyages can script the API to generate thousands of hyper-personalized assets at scale, maintaining their exact brand identity across every iteration. By defining the geometry through API parameters, the underlying diffusion model ceases to be an unpredictable creative tool and functions instead as a strictly controllable computational engine. Veo 3 is not designed to output a finished, feature-length narrative with a single click. It serves as a high-speed rendering engine embedded within larger hybrid production pipelines. This flowchart maps a standard enterprise workflow. It initiates requests through the Vertex AI Batch API, routes the raw outputs into an assembly tool like Google Flow to stitch the narrative, and terminates in a traditional nonlinear editor for final color and sound mixing. The pipeline requires this assembly step because the highest quality 3D volume calculation is hard-capped at an 8-second duration per generation. There are also constraints on the audio generation. While ambient sound effects generate with high reliability, complex spoken dialogue generation currently suffers from a high failure rate in the initial output. On the visual side, the physical rendering still struggles to accurately map complex fine motor movements, frequently distorting the anatomy of human hands and fingers. To mitigate these limitations and manage the computational costs of failed outputs, engineering teams rely heavily on batch processing and systematic prompt caching to lock in successful variables. Because these assets are deployed at an enterprise scale, every generated output also requires cryptographic provenance to meet corporate security mandates. Google implements a digital watermarking system called SynthID. It embeds imperceptible signatures directly into the pixel data, allowing the video to be cryptographically verified even after heavy compression and filtering. When you align the programmatic controls, the prompt syntax, and the latency constraints, you extract the true value of the architecture, the synchronized calculation of both visual physics and audio depth. Prompting has evolved into querying a spatial temporal simulator that calculates the physics of sight and sound as a single unified volume.